An automatic transmission, also known as an automatic gearbox, is a type of multi-speed transmission found in motor vehicles that can shift gears without any manual input from the driver during normal driving circumstances. Historically, the 1904 Sturtevant horseless carriage gearbox is often recognized as the initial true automatic transmission, while the first widely manufactured automatic transmission is the General Motors Hydra-Matic 2-speed hydraulic automatic, which debuted in 1939. These automatic transmissions are particularly favored in various vehicular drivetrains, notably in vehicles that undergo intense mechanical acceleration and experience frequent idle or transient operating conditions. This technology is commonly found in commercial, passenger, and utility vehicles, including buses and waste collection vehicles. Internal combustion engine vehicles rely on a specific range of rotation rates to function, in contrast to electric vehicles. This requirement necessitates the use of a gearbox, which can be either manually or automatically operated, to propel the wheels across a broad spectrum of speeds. In 2015, 43% of newly manufactured cars worldwide were equipped with manual transmissions, a figure that dropped to 37% by 2020. In the United States, automatic transmissions have a long-standing prevalence, a trend that took longer to establish in Europe. In 1997, only 10 to 12% of European cars were outfitted with automatic transmissions, while in the U.S., over 80% of new vehicles boasted this feature as early as 1957. Large cars in the U.S. have standardized automatic transmissions since at least 1974, with the popularity of manual transmissions dwindling to a mere 2.4% for new cars by 2020. Initially, automatic transmissions were deemed less efficient. However, in the U.S., lower fuel costs mitigated this concern compared to Europe. In the United Kingdom, automatic transmissions have become the norm for new cars since 2020, with prominent manufacturers like Mercedes and Volvo no longer offering manual transmission models. The increasing adoption of automatic transmissions can be attributed to the rising presence of electric and hybrid vehicles, as well as the ease of integration with safety technologies like autonomous emergency braking. The power output efficiency of conventional automatic transmissions typically falls within a range of 86 to 94%. Manual transmissions, on the other hand, excel in fuel efficiency compared to all but the newest automatic models. This efficiency stems from their inherently low parasitic losses, which hover around 4%, in addition to being more affordable to manufacture, lighter in weight, offering better performance, and boasting a simpler mechanical design. When it comes to fuel economy, a lower efficiency leads to a decrease in overall performance. Despite the advantages of manual transmissions, they require the driver to engage with the clutch and shift gears as needed. Real-world tests conducted in 2022 revealed that under typical driving conditions, manual transmissions deliver 2 to 5% superior fuel economy than automatic transmissions, a figure that can increase up to 20% with an expert driver at the helm. Although some laboratory tests may portray automatics in a favorable light due to the implementation of prescribed shifting patterns for manuals that are not always optimized for efficiency. However, during extensive highway journeys, manual transmissions demand the maintenance of a very precise cruising speed to optimize fuel economy, rendering automatic transmissions a more suitable choice. The most common design for automatic transmissions is the hydraulic automatic type, which typically employs planetary gear sets operated through hydraulic mechanisms. Unlike manual transmissions that rely on friction clutches, automatic transmissions are connected to the engine via a torque converter or a fluid coupling in older models. Rather than using gears along input, output, and intermediate shafts like manual transmissions, hydraulic automatic transmissions utilize planetary gear sets. To facilitate gear changes, hydraulic automatic transmissions employ internal clutches, friction bands, or brake packs, which lock certain gears to establish the gear ratio in use at any given moment. A sprag clutch, a mechanism that can freewheel and transmit torque in one direction, is often utilized for routine gear shifts, eliminating the need for synchronization during gear changes. The hydraulic controls for friction bands and clutches rely on automatic transmission fluid, ATF, pressurized by a pump and directed to the necessary components to achieve the desired gear ratio. ATF not only provides lubrication and corrosion prevention, but also acts as a hydraulic medium to transfer power within the transmission. Additionally, the main pump pressurizes ATF through a gear pump situated between the torque converter and planetary gear set, regulated by a governor connected to the output shaft that adjusts pressure based on the vehicle's speed. The ATF pressure is crucial for proper transmission operation. The valve body inside the transmission plays a key role in directing hydraulic pressure to the appropriate bands and clutches, managing various spring-loaded valves, check balls, and servo pistons. While older automatic transmissions regulated valve action using pressures from the pump and a centrifugal governor connected to the output side, newer models feature solenoid control, with gear selection overseen by a transmission control unit, TCU, or integrated into the engine control unit, ECU. Modern automatic transmissions have replaced the centrifugal governor with an electronic speed sensor that feeds information to the TCU or ECU. These advanced designs factor in the engine load at any given time, determined by throttle position or intake manifold vacuum. Despite early complexities that made hydraulic automatic transmissions more costly and challenging to produce and repair than manual counterparts, advancements in mass production and technology have significantly narrowed this cost disparity. In modern automatic transmissions, a torque converter is utilized for coupling and decoupling the engine, replacing the friction clutch found in manual transmissions. Between 1904 and 1939, various predecessors to the hydraulic automatic transmission were explored. The 1904 Sturtevant horseless carriage gearbox is often credited as the first automatic transmission for vehicles, with high gear engaging at higher engine speeds and shifting back to low as the vehicle slowed down. However, this early design was prone to sudden failures due to its inability to handle abrupt gear changes. The adoption of planetary gear sets marked a significant step towards modern automatic transmissions. Early advancements included the manual transmission in the 1901-1904 Wilson-Pilcher automobile from the UK, utilizing 2 epicyclic gears for 4 gear ratios, as well as the planetary gear set in the 1908 Ford Model T. Canadian inventor Alfred Horner Munro received an early patent for an automatic transmission in 1923, designed to use compressed air instead of hydraulic fluid. In the 1930s, hydraulic automatic transmissions began to take shape. The REO Motor Car Company introduced the self-shifter semi-automatic transmission in 1933-1935, which shifted between 2 forward gears automatically. Following this, in 1937, Oldsmobile released the automatic safety transmission, which shifted between 2 gear ratios in different ranges. The Chrysler Fluid Drive, introduced in 1939, offered a fluid coupling as an optional addition to manual transmissions, eliminating the need to operate a manual clutch. Moving into the period from 1939 to 1964, the General Motors Hydra-Matic emerged as the first mass-produced automatic transmission in 1939, incorporating a fluid coupling and 3 hydraulically controlled planetary gear sets. This innovation paved the way for automatic transmissions to be embraced by various car manufacturers, expanding to other brands outside of General Motors. As technology progressed, torque converters began to replace fluid couplings in automatic transmissions. The Buick Dynaflow, introduced in 1948, was the first to utilize a torque converter. This was followed by other 2-speed transmissions like the Packard Ultramatic and Chevrolet Powerglide. In the early 1950s, Borg-Warner developed 3-speed torque converter automatics for several car manufacturers, while Chrysler introduced the PowerFlight and TorqueFlight transmissions. General Motors also enhanced its Hydra-Matic transmission in 1956 for smoother shifts. By the mid-1960s, General Motors introduced the Turbo Hydra-Matic, a 3-speed transmission with a torque converter that standardized gear selections like park, reverse, neutral, drive, and low. The subsequent years saw an increase in gear ratios and the integration of electronics to enhance transmission control, leading to the development of transmissions with 4, 5, 6, 7, 8, 9, and 10 speeds to improve performance and fuel efficiency. The evolution of gear selectors, ranging from traditional layouts to electronic rotary dials and push buttons, also played a role in modernizing automatic transmissions for improved driver usability and comfort. A continuously variable transmission, CVT, offers a smooth transition through an infinite range of gear ratios, in contrast to traditional automatic transmissions with a fixed set of gear ratios. Controlled properly, a CVT can maintain the engine at a constant speed while the vehicle's velocity varies, allowing for optimal efficiency. CVTs find applications in a variety of vehicles like cars, tractors, UTVs, motor scooters, snowmobiles, and earth-moving equipment. The most common type of CVT utilizes 2 pulleys interconnected by a belt or chain, although various other designs have been implemented. On the other hand, a dual-clutch transmission, DCT, operates with two separate clutches for odd and even gear sets, resembling two distinct manual transmissions housed together. In most cases, DCTs function as automatic transmissions in vehicles, eliminating the need for manual gear changes. The initial production of DCTs dates back to the 1961 Hillman Minx midsize car with the Easy Drive automatic transmission. Subsequent adoption included Eastern European tractors in the 1970s and the Porsche 962C racing car in 1985, paving the way for the modern DCT seen in the 2003 Volkswagen Golf R32 and its increasing prevalence in the automotive industry, displacing hydraulic automatic transmissions in many car models. Alternatively, automated manual transmissions, AMTs, or clutchless manuals, are multi-speed transmission systems that automate aspects of the manual transmission process, such as clutch control, gear shifting, or both. Early variants like AutoStick operated semi-automatically, managing the clutch while requiring manual gear changes by the driver. In contrast, modern AMTs like Celespeed and EasyTronic function fully automatically, needing no driver intervention for gear shifts or clutch operations. Rooted in early clutchless manual transmissions from the 1930s and 1940s, AMTs aim to simplify gear changing for drivers of conventional unsynchronized manual transmissions, particularly in stop-start driving conditions. Pioneering models such as the Hudson Commodore's DriveMaster in 1942 and the Citroën DS's semi-automatic transmission in 1955 laid the groundwork for modern AMTs. BMW and Ferrari introduced early models in 1997 with the SMG and F1 transmissions, utilizing hydraulic actuators, electrical solenoids, and a transmission control unit, TCU, for clutch and gear control, often with paddle shifters for manual gear changes. Presently, the design of choice has shifted towards dual-clutch transmissions, rendering fully automatic AMTs like Celespeed and EasyTronic somewhat obsolete.